0 plus plus are two symbols, they represent the same natural number. Something like that. It's like the same person has two names. It's like that, in that sense. So if they are given, then exactly one of these three conditions is true. Either A is greater than B, or A is equal to B, or B is greater than A. This is called the trichotomy for order relation on the natural numbers. And this we are going to prove. Okay, so for this, what do we have to prove? First of all, let us show that none of these, no two of these three conditions can occur simultaneously. So we write the proof. So let us first show that no two of the three given conditions can occur simultaneously. Is that the way we have proceeded? Yes. Okay. If A is greater than B, then by definition A is not equal to B. Because A is greater than B means A has to be greater than or equal to B, and A is not equal to B. Okay, so from the definition of this relation, this thing simultaneously cannot happen, so it cannot be true. Similarly, if B is also greater than A, then by definition B is not equal to A or A is not equal to B, same thing. So this and this cannot simultaneously occur. This and this cannot simultaneously occur. What about this and this? If A is greater than B and B is greater than A, then A is, first of all, we write the meaning of this, okay? A is greater than or equal to B and A is not equal to B. And then we write the meaning of this. B is greater than or equal to A and B is not equal to A. Now from these two relations, this one and this one, we have the fact that A is equal to B. Where is that coming from? That is coming from anti-symmetry, the thing that we have already proved in the previous result. But anti-symmetry then implies A is equal to B. You know where anti-symmetry is coming from these two conditions. This is a contradiction, and what is being contradicted? Because we are already given that A is not equal to B. Here, however, we are getting that A is equal to B. This is a contradiction. So, both A greater than B and B greater than A cannot be simultaneously true. Okay, so in this part we have proved that no two of these three conditions can happen simultaneously. But now we have to prove that in any case, at least one of these conditions will be true. That will tell me that exactly one of the conditions is true in any given case. So in the next part of this proposition, we are going to prove this. Now we prove at least one of the three conditions is true. Now this again we will do by induction, and we will apply induction on A. For this, we apply induction on A. Now here I will just write the proof verbatim to what is given in the text. There is a reason. Okay, the reason will become apparent pretty soon. By induction on A, keeping although not verbatim, but the logic I will keep the same. A keeping B fixed. Okay. So let us just once more try to understand what we are going to prove here using induction. If A and B are given to me, then I have to prove that I have either this to be true, or this to be true, or this to be true. And that statement I am going to prove by applying induction on A, keeping B fixed. Okay, this is what I am going to do. So naturally I will first of all look at the case when A is 0. When A is equal to 0, we have 0 is less than or equal to B, and in the text there is a question attached to it. Why? Okay, these whys we have to answer. That's why I said I have to see what the text writes. Assuming that these why questions have been answered, there are more, we proceed with the proof. Okay, so when A is 0, we have 0 less than or equal to B. You see, this is something that we already know from our previous knowledge about natural numbers, but we have not yet proved this. Keep that in mind. So we have to justify why this is the case. So that will be done after we finish the proof. Okay, so we have zero equal to B or 0 less than B. From this, how are we getting this? You see, we have 0 less than or equal to, or I am using less than or equal to, although I have not defined the phrase less than or equal to, but you understand what it means. When we say A is greater than or equal to B, that is the same thing as saying that B is less than or equal to A. I could have written that in the definition when I defined order relation, but I did not do it. So when 0 is less than or equal to B, I have two possibilities. Either 0 is equal to b or 0 is not equal to b. One of these two possibilities is true. That is evident. If 0 is equal to b, then I have this. If 0 is not equal to b, then along with this inequality, these two things tell me that 0 is strictly less than b. Again by definition. That's how I am getting this. Okay, now what have I achieved here actually? For the case a equal to 0, either a is equal to b, that means either this is true, or a is less than b, that means this is true. So that's what I have to show, right? At least one of these conditions is true in any case. So my claim is true when a is equal to 0. This is the basis for my induction. Now assume that now next I am going to assume that the result is true for some natural number a. Now assume that at least one of the following conditions is true. A is less than b, a is equal to b, a is greater than b, or b is less than a, where a is some natural number. So this is my induction, this assumption is my induction hypothesis, which has been made for some natural number a. Keep in mind that b is fixed. Okay, b stays fixed, we are changing a. We now have to look at the case when we replace a by its successor. Okay, and I am going to start with these conditions one by one. If a is less than b, then the properties of natural numbers the properties of order that we have proved just now in the previous result, that allows me to write if a is less than b, then a plus plus is less than or equal to b by what was this part? This was part E, I think. Is it part E? Yeah, this is part E, by proposition 2 to 12. This, yeah, 2 to 12. 2 to 12E, let me write it like this. This means by part E of proposition 2 to 12, when we have this, we have this. So you see that I have got a relationship between a plus plus and b. And from this relation I can draw the conclusion. So either, just like what we did here, after writing 0 less than or equal to b, I have written, so we have 0 equal to b, or why did I wrap this up? 0 strictly less than b. Similarly here, a plus plus is less than or equal to b, so either a plus plus is equal to b or a plus plus is strictly less than b. Okay. So among these three conditions, I already have two when we have a plus plus in place of a. But this is when we have this. When we have this, I need to carefully at the same time also make sure that I mention the why parts, because that constitutes an exercise. Note that we have to still answer this why. So like that there are two more whys. If A is less than B, okay, so here there is no why. If now if A is equal to B, then A plus plus is greater than B. This we have to explain why. And one more condition is there if B is less than A. If B is less than A, then A plus plus, again A plus plus is greater than B. Why? So assuming that these whys have been answered, now I have the proposition, I have the result when I have A plus plus in place of A. So this completes, or to make it more clear to you, that is, in any case, at least one of the following three, I am losing ink. Let me just refill it quickly. Give me a moment. So the following three conditions, so that is in any case at least one of the following three conditions is true. What are the conditions? A plus plus is less than B, A plus plus is equal to B, and A plus plus is greater than B. So this is the induction hypothesis. This is the same thing when we have A plus plus in place of B. So that's what we have in every case. This completes the induction. And we have proved that in any case at least one of these three conditions is true. But in the first paragraph we proved that if no two of these three conditions is true. So exactly one of these three conditions is true in any case. Okay, now we answer these whys. And that is an exercise in itself. And that is exercise 224. And the exercise says this: justify the three statements marked Y in the proof of proposition 2 to 13. So this is the exercise. We will now solve this. We just have to answer why these three things are true. So here is the solution. Why do we have this? Okay, you see, b has to be shown to be greater than or equal to 0. That means we have to find a natural number which when I add to b, which when I add to 0 I get b, and clearly that is b itself. Since b is equal to b plus 0, or keeping the order of the things intact in the definition, b is equal to 0 plus b, we have 0 less than or equal to b. So that is the reason we have this. Okay, next comes this. If a is equal to b, why do we have this? Since a is less than a plus plus. You see, we have already come across this once when we said that there is no largest natural number. There we have proved this or made sense of this. Since this, we have if a is equal to b implies b is less than a plus plus, or a plus plus is greater than b, same thing. Finally, we have this point. This is also easy. If b is less than a, then b is less than or equal to a and b is not equal to a. Okay, this is the meaning of b being less than, strictly less than a. Since we also have a less than a plus plus, which means a is less than or equal to a plus plus and a is not equal to a plus plus, we have, okay, look at these two relations. b is less than or equal to a and a is less than or equal to a plus plus. Using these two, we can write b is less than or equal to a plus plus. Why? By transitivity. It's one of the proposition 2 to 12 part B. Okay, it's because of that we are able to write this. Okay, so we have got this, and at the same time b cannot be equal to a plus plus. Why? b is not equal to a plus plus because if b becomes equal to a plus plus, also b cannot have b equal to a plus plus, as otherwise if b is equal to a plus plus, then you use this relation here, remember for this one we are starting with this. Okay, otherwise a plus plus is less than a, and trichotomy or trichotomy is, oh, I cannot write this. No? I cannot write trichotomy is violated because I am still in the process of proving the previous proposition. The y's have to be answered, then only the proof will be over and I can use trichotomy. So I cannot write this. I cannot give this justification. The justification that I will give is this. And this contradicts the first paragraph of the previous proof, because we already know that a is less than a plus plus. So what have I written here? You see, I am saying that I cannot have b equal to a plus plus, because if I have that, then in place of b, if I write a plus plus here, I have this. But at the same time, I also have from a previous result that a is less than a plus plus. This allows me to say that there is no largest natural number. There I have proved this. Now if I have this and at the same time I have this, then this violates what we have done in the first part of the previous proof, in the first paragraph. And in the first paragraph there was no y. It was proved independently of anything that we are doing here. And what was proved? It was proved that if we are given two natural numbers, then no two of these three conditions are simultaneously true. So you apply that thing to these two natural numbers, a plus plus and a. Now here we see that if I write a plus plus in place of b, then I have this, and at the same time I have this. And in the first paragraph I have proved that these three things, any two of these three things cannot happen simultaneously. So that has been violated. So that's why I cannot have this. So that means what do I have now? So we already have b less than or equal to a plus plus, and we also have b not equal to a plus plus. That is, b is strictly less than a plus plus, and this was the last one. So this completes the solution, and now the proof of trichotomy is over. That we have given the we have answered the three y's. Okay, now we have introduced order relation, greater than or equal to, less than or equal to. They help us order the natural numbers, which one is larger, which one is smaller, that thing. So now using these properties of order that we have proved, we can now state a stronger version of the principle of mathematical induction. You see, you recall, I have already said that there are some other versions of the principle, the fifth principle of piano, and they are the strong induction principle, backwards induction, and transfinite induction. So the time has come that we state the strong induction principle and prove it. And for that, to state the strong induction principle, we need this relation. So that's why we are able to state it. And the statement goes like this. Proposition 2 to 14. And it's called strong principle of induction. We will see why it's called strong. And the statement goes like this: let M naught be a natural number. So let M naught be a natural number, and let Pm be a property pertaining to an arbitrary natural number. M. Okay, so M naught is some natural number and Pm is a property pertaining to an arbitrary natural number M. Suppose Pm satisfies the following condition. There is a restriction on the property Pm. Previously also, in our actual mathematical induction, actual principle, the fifth one of piano, given by piano, in that also we have restricted Pn. So here also we are going to restrict Pm. If Pm is true for all natural numbers M satisfying these inequalities. See, to write these inequalities, we need the order relation. M less than or equal to M naught less than or equal to M strictly less than N. If Pm is true for any natural number M satisfying these inequalities, then Pn is also true. Then Pn is true. Okay, so this is the condition we are enforcing on Pm. If this is the case, then the conclusion of this principle is that then Pm is true for all natural numbers M greater than or equal to M naught. This is the conclusion. It looks somewhat like the principle of induction, the ordinary one given by piano, but it is different in that it assumes the truth of not just Pm, what I'm trying to say is this. Suppose you have a natural number n, and you have, or let me write it like this. Suppose you have a natural number m, and you have the successor m plus plus, which comes next, and that is suppose equal to n. Okay. Instead of just assuming that Pm is true, to prove that Pm is true, or instead of assuming that the truth of Pm implies the truth of Pm plus plus, we are assuming a stronger condition. We are assuming that Pm is true for all m lying between m0 and the number before n. Okay. So because the hypothesis is stronger than what we usually assume in our mathematical induction, that's why it is called strong principle of induction. This version of induction is also sometimes used, and without this it will be difficult to apply induction to some processes. Of course, if we apply this result, then we are not really applying induction, we are applying principle of strong induction, which is a different result. So now we will, but by the way, there is one more point about this that I should mention. Note that in this statement there is no mention of basis. Unlike the usual induction